Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this short clip we look at how the rate of a typical reaction changes over time and then go on to use collision theory to explain why the reaction rate changes in the way it does.
At the beginning of collision theory, we looked at how we measure reaction rates, and one of the ways is by the volume of gas being given off, remember. There are other ways, and from that we can actually draw a reaction profile. And a typical reaction profile looks something like this. You've got a steep curve that gradually gets less and less steep until it goes horizontal like that. And the most common reactions, not all reactions do this, but the most common ones that we encounter do this. So this is telling us something that they're all behaving in a similar way when they're reacting. So it's a good idea to rationalise what's exactly going on here. And you've done this last year at level 1, and you are expected to be able to do the same thing this year. Okay? You can explain why these curves do this using collision theory. So the first thing we need to do is remind ourselves is what information can we get from that graph? It's just a graph with a curve to it. What's the sort of information we can get from that that will help us? So we can get the rate of reaction at any point by just drawing the gradient. Okay. So why don't we write that just down the side here? Okay. So any information about the reaction rate is given by the gradient of the line at any point along that line. Okay? You can get that, some of you are probably doing it now, by using calculus. Okay? Because it's a non-linear curve. You use calculus, you differentiate the equation for that curve, and at any point you can work out its gradient. But we don't need to do that. This is more about interpreting what's going on in terms of change rather than absolute values. So what we can do is split this typical reaction up into 3 sections. Okay? First section is right at the very beginning, then somewhere midway along, and then right at the end. And we'll look at each section in turn. Okay? So let's start off with section A. What can we say about the reaction rate and why?
Fastest.
It's its fastest. And how do we know that? Steepest gradient. So let's write that. So it's as simple as that. That's what the graph is telling us. Nothing else. It's just telling us we've got the steepest gradient here, so the rate of reaction is at its fastest rate, basically. Why? Why? Why is it at its fastest rate? Exactly right. So he's gone to the factor first, and then you have the explanation. So always start with what is the thing that's leading to, what factor is it that's giving the fastest rate? And that is you've got your highest concentration of reactants. Got the highest concentration of reactants, highest frequency of collisions, highest frequency of effective collisions, fastest rate. Okay, so very nice and straightforward. Should we write that down? And then we move on. Okay. So that's section A. So we've got the highest concentration of reactants, the highest frequency of collisions, the highest frequency of effective collisions, and so the fastest rate. So if we now go on to section B, where the reaction's been proceeding for a period of time, then what's happening to the concentrations of the reactants? They're going down because reactants are being used up. Okay, so as the reactants are used up, the concentration of those reactants goes down. So what does that mean in terms of collision theory? Why is that not a good explanation? Why is less collisions not good?
Oh, because there's other.
Less frequent collisions.
That's better. Okay, you must put in the time factor. So there's a lower frequency of collisions, or less collisions per unit of time. You must put in that time factor. So there's less collisions per unit of time, less frequent collisions, less frequent effective collisions, therefore a slower reaction. So it's slowing down. Okay, so let's write that down. So the important thing there is that the concentration of reactants is going down, which means the frequency of collisions and therefore the frequency of effective collisions is going down, so the reaction is slowing down. Remember, everything comes back to the frequency of those effective collisions. Okay, section C is fairly straightforward, but it's important you appreciate it's when the line is horizontal that we're talking about the reaction stopped. Okay, so horizontal line means that the reaction stopped, and that's just because one or both reactants has been used up. Okay, one final thing to bear in mind is if we change the conditions, so for example we increase the concentration, increase the temperature or add a catalyst, how would the line compare? It would be steeper. So there's two things to bear in mind, okay? And these are two things that often happen. People often will draw a second line in and it goes above the first, okay? You should never do that because you're going to be using exactly the same quantities. If you're going to do a fair comparison, then you start with the same quantities but either change the concentration of one of them, or you will heat it up or add a catalyst or whatever. So you're going to get the same volume of gas off at the end. So that's not going to change. The other potential issue, and this is what happened with a lot of people last year when they were asked to do this in a question, is they draw the line, so it's steeper to begin with, but it gradually, and it just about touches the line as this one is going horizontal. That is completely wrong, because what you're doing is you're speeding up the rate of reaction, so it's going to finish before the one in black here. Okay, so the line must be horizontal because the reaction stopped before this one stops, and before this one's horizontal. Yeah. So a correct line, which I'll do in green, would start at the same point, would be steeper and would go horizontal earlier. So you've got this sort of hump effect here, not going higher, of course, you're not going to create more gas. But it's horizontal before it's that line there. And that was the biggest mistake that people were making. They sort of like intersected, but still both going up at that same point, when it should be that this is horizontal beforehand. Does that make sense? So don't make that mistake if you are asked to put a second line on. And be careful. Don't always assume. We always sort of show you what happens if you add increase the concentration. They might ask you something where you decrease the concentration. Okay, so you would have to do the bottom line equivalent. So make sure you get it the right way around.